All right, welcome everybody. We're gonna kick off this series of doing science experiments at home with the diffraction phenomenon. So I've pulled up a screenshot here of a Google Images search for single slit diffraction from water waves. And you may or may not have noticed in your times at the beach, here we are in the summertime. I'm sure you've been to the beach before in the summer and are about to head there again sometime soon this summer, you might have noticed that if you have like an eddy or like a harbor sort of barrier set up here or here, you'll see that you have these pardon me, you'll have waves coming in and they're like parallel. They're like forming walls straight lines. And then they come to the barrier and they spread out. They form circular, like semicircular patterns. If you could see here where my mouse is, that's called Huygens principle. It means essentially that as a plane wave approaches a opening in an obstruction, that obstruction will act like a new source of light, as you could see over here. And so they fan out. It's due to a phenomenon called diffraction, and it essentially means that the wave begins to interfere with that obstruction and bend around it. And you could have multiple slits as well. Something interesting happens with multiple slits, but we'll just look right now for one slit. So the equations, so here's just a little bit of math. Over here on the left, you'll have the barrier and then this opening here, which is length A. Let's call that A. I just grabbed this off of Google. And then you have a screen some distance D, capital D, perpendicular distance from the light source. The new light source due to Huygens principle will be right here, even though the laser that we're going to use will be way further back here. And so you'll notice in a moment, you'll see a pattern of bright and dark patches that go along the screen. The reason for that is light is also a wave. Um, just like water waves are a different type of wave, light waves, also being waves, exhibit the phenomena known as diffraction. And so what happens here is when the wave crests overlap, they constructively interfere. That means they add up. And where a crest and a trough coincide on the screen here, they will cancel out and you'll have a dark patch. The dark patch just means there's no light there. And red or whatever color laser you're using will be bright wherever the crests add up. And so this wavy pattern here, if you could see my mouse, that is where the theoretical predictions for the amplitude as a function of distance from the center point. So you're going to have a very bright point of light in the center directly perpendicular to the midpoint of your opening, A, and then you'll have decreasingly brighter patches as you go either up or down from the center point. And it's symmetric, as you could see from the plot. So you'll end up with the same brightness here as you do at its mirror image point on the opposite side of the perpendicular bisector. And really there are more and more, not just three. This is just a cartoon image I borrowed off of Google. So this equation here relates the distance y, that is the point from the middle of the center bright patch to the middle of the, actually they've drawn it here to the end point of the next bright patch, that's y. M is just an integer, 0, 1, 2, 3. Um, and so we're going to, it's called the order. We're going to take m equals 1 today. And then lambda, that is the Greek letter lambda, that is the wavelength of the light, which is what defines the color of the laser. and then D here, and then A. So y equals, remember m equals 1, so y equals lambda times D over A. And you could rearrange this with some simple algebra and find that A equals lambda D over Y, just by cross multiplying there. Okay? So here's my experimental setup. I used my bed and my nightstand. So I have this really beautiful green laser that I bought, and it has a known wavelength of 532 nanometers that's set by the manufacturer. And I put an old cell phone, it's the iPhone 12 here, and sort of inclined it and shone the laser light on it. Now the screen was off, the phone is off, and yet the pixel array on the screen acts like an opening. You have a green pixel here, a green pixel here, and the distance between them, that is set by the manufacturer of this iPhone. So we'll come to that here in a moment. So here's from a different perspective. I have this rope that I use to prop up the phone so I could get a nice angle. You can see the beam of light coming off of it here. And here is the other perspective. You'll see the center point. Remember I promised you that the center point is the brightest one. We go back here. This peak here is taller than the other peaks, and the amplitude determines the brightness. So here's where the laser essentially reflected off, constructively interfered with itself. It's technically not even reflecting. It is, but in this case, it's actually also diffracting. This bright point here is the combination of constructively interfering waves. And you'll notice, of course, this array of dark and bright patches. Let's take a closer look. So here, the reason why these are in a circular pattern, and there are a bunch of them, instead of the linear version like you have here, is because this is just for one slit. But on an iPhone, you have a whole grid, a two-dimensional grid of mini slits. And so you have to keep in mind that you're going to get a lot more than just one series. One of these arcs here would be if you just had one row or one column of pixels instead of a rectangular grid of rows and columns of pixels. But that's okay, we could work with this. So what I did was I took some paper and I put it on my wall, and you can see I took a pencil and just marked the center point. I just did a few of them. Really, all I needed to do was measure these two here, the center of the bright one, and maybe a couple on the other side, because we're going to take some averages to increase our accuracy. And here's a little bit of a closer look. I didn't quite get them exactly in the center, but that's okay. There's always experimental error. So what I have next is a spreadsheet on Google Spreadsheets, whatever it's called. And I have taken the distance from the diffraction grating to the screen, capital D, and I measured that at 62 and 10/16 of an inch. And I did that very carefully. That number also has some error associated with it that I did not quantify at this time. I converted that into centimeters because we're scientists. We use centimeters. I don't bother with inches. And next we have the laser wavelength given by the manufacturer. In nanometers, it's 532, and it looks like this in meters. And then we have the distance between the adjacent maxima that I measured carefully. And I did a couple on either side of the central and averaged them, and I got 1.59 centimeters. And so if you do all that, you find that so we have this big number here is just to accommodate the nanometers and centimeters and get it into eventually what I want is microns, or 1/millionths of a meter. So I got 53.31 microns, and here's the equation if you recall. So it's just we're solving for A, so it'll be lambda d over y. And so I measured these, and except for lambda, which was given to me, and I get 53, let's just say 0.3 microns. And so what's interesting is I actually looked up the iPhone manufacturer's um, information on what it really is. The pixels are 0.055 millimeters apart, and that is, if you move the decimal over 3 times, 1, 2, 3, 55 microns. So let's take a look. So the manufacturer says 55, and I got 53.3. Not too bad. That's about 3.1% error, and that is pretty good considering everything. So the next part is to take a red laser, and this one does not have a known wavelength. So we had to now take the information from the A, that distance between the pixels, and calculate, or rather experimentally measure the wavelength of the red laser light. It was the same D because I didn't change the setup. This number here was measured from the previous part of the experiment, and then the Y, the distance between maxima, I experimentally measured and found it to be 12/16 of an inch, or 1.91 centimeters. And I got a result of 638.4 nanometers. We could just call that 638. So now that I know the distance between the pixels, I've measured the wavelength of this red light. I'm going to now use that red light to measure the thickness of one of my hairs. So let's first take a look at my experimental setup for, actually before I do that, let me just show you. So here's the experimental setup for my red experiment. There's my red laser. Same distances and everything. And except for, you'll notice, the distances between the maxima of the resulting diffraction pattern. It might be hard to tell from the picture, but it's different than the one for the green. It's necessarily different. Okay, so now for the hair part of my experiment, I took one of my hairs. You could see it right here. I took some paper and cut out a little rectangle in here, and taped one of my gray hairs, not one of my brown hairs, to this thing and set up my red laser here. And that laser light, we now know, is about 638 nanometers. And I had to sort of line it up carefully so that the laser was hitting just this one hair, the thickness of it. And when I did that, I got a diffraction pattern that should look a little bit familiar to you. In this case, I don't have a two-dimensional array like we saw with my cell phone, because a hair is just one diffraction grating instead of a two-dimensional array of many of them. So we expect this line of bright patches. And so I measured the midpoint of a few different adjacent maxima and found their average. And when you do that, when I did that, I found, oh yeah, also the distance had a different, there's a new experimental setup, so there's a different distance to the screen, and I measured that. I measured the distance between the maxima, the Y value, and we know from the previous part of the experiment that the wavelength is this number, roughly 638 nanometers. And I measured so it was about 6/16 or 3/8 of an inch between the maxima. Here's that same number in centimeters, and I'm just going to tell it to use this value and calculate. There we go. So the hair, did you see that? So as I type in, so I tell Excel to just grab this number for my Y value and watch. So there we go. This number was nothing, and now we have we have just experimentally measured the thickness of one of my gray hairs is 76 microns. So let's just do a quick check and see how close that is to what we would expect. So let's just say, how thick is most hair? And okay, so this is from 16 microns. We're moving the decimal over 1, 2, 3, from 16 to 50. And actually, I've seen, here we go, it can be anywhere from 80 to 200 microns. And this one says from 30 to 60. Yeah, so the very general range is, depending on the hair, from 80 to 200 microns. So let's go back to the spreadsheet. Where was that? Over here. So they said from 80 to 200 microns. 200. And mine was right there on the low end. And really, it really could be as low as 30. I think that's what it said. 30 to 200 microns. So mine is, my gray hair was a little bit on the thin side. And depending on what kind of hair you use, you're going to get a different result. They say that like beard hair is generally thicker. It could be fun to try this experiment with different hairs and see what you get. But anyway, there you have it. The first episode for doing science experiments at home with only things you have available at home. Here's one of my hairs. I'm using it as a single slit diffraction grating and some laser pointers I have at home. I hope you enjoyed this. Please let me know if you have any questions and stay tuned for another episode.